No, one moment. There we go. It's a great pleasure to welcome Louis-Hadrien Robert from Geneva, who'll be talking about symmetric Khovanov-Rozansky homology. And I'll make the announcements at the end of the lecture. I don't like to start things off with announcements. It's very so take it away.
All right, thank you, Ben, and thank you for setting this QUACKS conference up, or keeping it with the COVID situation. I'll have a kind of a low-tech setup for my talk, but I hope you will be following nevertheless. And so please interrupt if you have any question. And if you feel that I should write bigger or whatever, then please tell me. All right, so I'll be speaking about symmetric Khovanov-Rozansky homology. So it's a joint work with Emmanuel Wagner. The paper which referred to this work is available in the archive. And and the aim of this work is to categorify the Reshtikin to IF invariant associated with symmetric powers of say standard representation of UQ SRN. Okay, so I should mention here that there are other approaches for that. So, for instance, by Khovanov. So, yeah, maybe let me tell you that for n equal 2, this means that we are really interested to the Color-Jones polynomial. Okay, and so there are other approach by so Khovanov, by Ogenkamp and Cooper, Krushkal and Cooper, I think, but I won't speak at all about that. And what I'm speaking about is related to, but I won't speak neither about that, related to work by Kautis, and Kefelec, Rose, and Sartori. Okay, but I won't speak about that. And let me maybe mention why this would be important to actually categorize this symmetric powers. Because one reason is that for the Color-Jones polynomial, at least, this is the Color-Jones polynomial actually appear in so Color-Jones appear in the definition of the Witten-Reshtikin to IF invariant of through manifold. Okay, so when I say Reshtikin to IF invariant, I really mean like link invariant or oriented link invariant, and with WRT, I really mean the through manifold invariant. So the plan is as follows, it's not exactly the plan because as we'll see, but so first I want to recall what is known for exterior power. So which I will denote like this. So wedge power. Okay. And then I will try to explain how to adapt it to sim. And somehow the talks will be, so this is kind of a proto plan, and actually the real plan is to first deal with just the RT invariance, so the decategorified story, and then to go to the categorified story, so categorification. So this big one and big two will be separated in small one and small two. Yeah. So, all right, and so so I'll start with Reshtikin to IF invariant, and well, I will at least speak a lot about Moy graph. So maybe I should say that Moy is for Murakami, Otsuki, and Yamada. So this, and so here I will assume for simplicity that n is greater than 2, and yeah, actually n equal 1 will do as well, but just okay. So, and what I want to actually explain is not, I mean, you all probably all know the Rechtlich-intuitive invariance, I just want to explain how I think, how I compute it, okay? And I'm really, in this way, following Murakami, Otsuki, Yamada. So I take a link, L, and so this should be oriented. And if I want, it's colored. So, and the color are, so between 0 and n, okay? And the Rechtlich-intuitive invariance takes this data and produce, so maybe I should put an n here, a Laurent polynomial in integer coefficient. Okay, maybe I'll do that. Okay, so and the point is this three Japanese guys, Murakami, Otsuki, and Yamada, they explain how to forget about representation theory. So, which is not necessary. I'm not claiming that this is a good thing to actually not think about representation theory. I'm just claiming that somehow they give combinatorial insight which are useful when you try to categorify. And this is why I want to focus on this, because this is what is important for me afterwards. All right, so I'll go further now, and yeah. So the idea is, so you start with a diagram. Start with a diagram, okay, and so this diagram is of course so colored and oriented, and replace formally a crossing like this with, say, I don't know. So this might be two different components. So maybe these links are, I mean, this component are colored differently. So let me call them N and M. And I replace this guy by a formal linear combination. Okay, I don't want to be too precise of what I mean now, but just so you should really think of this as a recipe more than anything else. And so you have some like normalization term, and then in the end, you replace your crossing by this kind of square. So you, okay, let me try to be consistent here. So N, M, N, and M. Here you have K, here you have N minus K, here you have N, M plus K. Oh, of course, okay, I did everything wrongly, okay. So you have N plus K, M minus K, and here something clever, N plus K minus M, well, whatever. So you, yeah. And so so when you see the other crossing, so the, then you basically do almost the same thing, except that the Q power here is M minus K. Okay. Right. So this is so for the moment it's not clear at all where these guys live. Okay, but yeah, but this is well, as I said, it's just like a cooking recipe, so it's fine. Okay. So now we may wonder, okay, so what do we obtain then? So we obtain a big linear combination of Moy graphs. And so I should explain what Moy graphs is, what Moy graphs are. So these are labeled or colored if you want, but somehow oriented, trivalent, and plane graphs. Okay, so so this is really what we see here. So we see that everything is trivalent, and it's definitely plane because we kind of remove. So it's plane, meaning that it's embedded, not only embeddable but really embedded. Okay, and we see as well. I don't know if you, I mean, probably my handwriting was too bad for that, but we see that there is a kind of flow condition here. So the labeling and the orientation satisfy some kind of flow condition, meaning that all the vertices, they look either like this, so they kind of merge two input into one output, or on the contrary, they split one input into two outputs. Okay. So that's it. All right. So so now I still don't know how to compute my sticking to invariant, but but that's somehow in the paper of maybe I should write the name and pattern for real. So Murakami, Otsuki, and Yamada. They explain how to associate with a graph gamma, so my graph. Well, I should maybe put a real stuff here. A bracket, okay, which will depend on n, which actually lives in Laurent polynomial with integral positive coefficient. Okay. All right, so I will explain. For this, I kind of should give a set of rules that I will actually display now. Okay. So they tell you that, okay, so you will see, you have this this graphs, and now you have a set of rules which actually are enough to actually compute everything. Okay, and so maybe I should say here that when you see k, this means qk minus q minus k divided by q minus q inverse, and well, that the quantum the factorial is as usual the product of k of I, and binomial satisfies the usual thing. Okay, so nothing really surprising here. So yeah, so you have this set of rules, and so I should actually, I will tell you why it's actually, so these rules are actually enough to compute everything, and they are consistent, and the consistency actually follow, I mean, can follow if you want it from a representation theory, but I'm not really interested in the consistency, because I really see this as a cooking recipe. So somehow I take for granted that everything is well defined. All right, so maybe just to give you a little insight of what this kind of quantum of this Laurent polynomial actually are. So maybe this guy here, you should think of it as a so maybe I should say kind of quantum dimension, or maybe I should say just Poincaré. Okay, Poincaré polynomial of the cohomology ring of so Grassmannian of k-plane in Cn. Okay, so just like this numbers are not just random. They're kind of very nice, and so you may have a lot of insight from geometry. I don't understand algebraic geometry, so it's for me it's a little bit useless, this kind of thing. But so these numbers are very nice, and so you can interpret some of these things are being like coming from some kind of fibration or whatever. So there are many things you can say with this number, and which are very nice. But I don't want to go into much detail about this. All right. So I should probably mention. Okay, so I want to be a little bit more careful. So yeah, as I said, so these rules are consistent. So this is a first thing. So this follow from representation theory and so on, and they are enough to compute. And this is why somehow you can forget about the representation theory. And this is, I mean, this was kind of well known by the community, but this was proved by Hao Wu, I think 2007. I mean, this was formally written here. So, all right, so this was for the like exterior power ID. And so now if you want to go from exterior power to symmetric power, so I didn't say anywhere why this was kind of exterior or whatever, but if you say, believe me, and maybe if you are good with the presentation theory, probably you guessed it by yourself. But so to go from exterior to symmetric, the idea, well, you can use kind of the same recipe. So for the crossing, you use exactly the same rule. So same rule. And but you change a little bit you change a little bit the well, the rule for cooking the Laurent polynomial associated with graphs. Okay, so okay, maybe I can just to compare a little bit. So I don't know if this was probably not very clever, but anyway, so so basically what's changed, the only thing which changes when n appear on this formula, then somehow things get a little transformed. But say for instance, here we have no big N coming, and so the relation stays exactly the same. Yeah, and so and if you, I mean, you can kind of interpret this process. I should put some yeah. So basically what we do is we take N and we put it to minus N. And so this has something to do with going into a supersetting or whatever, but I don't want to discuss this too much because I'm actually not exactly doing that, because if I would do that really, I would have some sign and so on. I just got rid of signs, and so I'm not exactly doing that, but yeah, so somehow a good approximation of what would be the cooking recipe is just replace N by minus N in the previous formulas. And somehow this proves that the rules are consistent, and that they are enough to compute as well in this case. Okay, so the rules are basically the same, and so on. All right, so that's it for that's it for the decategorified story. Okay, so now we'll move to categorification. All right, so and so I will present. So here, so be careful. I am very biased in what I'm going to say. Okay, I want to present things so that it fits what yeah, the rest, but the rest of the talk better. So so if you don't like to think about Khovanov homology, like I will explain, that's probably normal. It's just that I need this point of view to actually go further. Okay, so just so the simplest case of so Khovanov, the simplest case of this categorification is Khovanov homology, and this is for n equal 2, and then there is this Khovanov-Rozansky homology. This is for general n, and somehow in both, well, in my opinion, there are kind of 3 steps which are needed to actually define this guys. So the first step is Ricard complexes, and so and this. So if you're familiar with Khovanov homology, what I mean is just the idea of this RPQ. Okay. Then there is a second step, which is picking a nice, maybe I should say, kind of TQFT. Okay. And then the third step is just basically like playing with homological algebra, just to make sure that actually the RPQ is, if you want, a complex. So yeah. So what I will be focused on today is really try to well, the last step is obviously kind of standard because it's called homological algebra. There are textbooks about that. And the first one is not completely, I mean, it's not as standard as just dealing with complex homological algebra. However, it's rather standard. So what I want to focus on is really this nice TQFT. All right. Okay, I still have 5 minutes before the, yeah, okay, great. Okay, so, and I won't, okay, so I won't define for you Khovanov or Khovanov-Rozansky homology. I just want to focus on this part of the story here. Okay, so in our context, remember that we work with this, so what I explained before is that we have all these small graphs and so on. So in our context, the source category, as for object, Moy graphs. Okay, so if you are familiar with Khovanov homology and maybe by the description of it by Barnaton, then somehow this replaces the category of which consists just of collection of circles. Okay, yeah. So, but now we are in this SLN case, so we have deal with Moy graphs. Okay, and then the question is, what are the morphisms? Okay. And the morphisms, so I need to find another piece of paper. So the morphisms, well, the answer is foams. Okay, so foams, maybe I can do something like this. Foams. Okay, so foams, they are what will replace surfaces. So if you were working with circles, then morphism between this circle would be obviously like surfaces with boundary. Now we have this Moy graphs that you can think of as like one manifold with some singularities and actually with some extra data such as orientation and labeling and so on. Okay, but it's kind of reasonable to think about morphism between such things as just being like surfaces with some kind of singularities. And there's some singularities you definitely want to see because, for instance, if you have a Moy graph, definitely this Moy graph times the interval should be a morphism. It should be the identity morphism for your Moy graph. So this means since we have since in Moy graphs we have kind of this trivalent singularity, it's clear that we want to have some kind of a tripod times interval type singularity. Okay, and actually we want something a little bit more complicated as well. I'm not sure if this is surprising or not, but we have this kind of more complicated singularity. So I'm not sure if you can actually understand anything here. But let me draw something here. You have this more complicated singularity here, which is simply a cone over like the tetrahedron. Okay, so cone of this, cone over. Okay, another way to actually draw this is so you take imagine you have a ping pong table, a tennis, tisch tennis, a ping pong table. And so you have a table and a net, and you put an extra net, you see on the back of it. Yeah, and so you have exactly the same picture, okay? And well, and there are extra, as I said, there are extra data there. So you have labeling, and they satisfy some properties such as you see a flow condition exactly as for the graphs and so on. And well, yes, that's it. And then so yeah, and there is an extra piece of data which is important. I wrote this here. So plus decoration. So decorations, what they are is, so it's a little bit more involved here. So as I said, I have the facets of my foam. They have some labeling, and so decoration on a facet of label A is a symmetric polynomial in A variables. All right. So this is kind of the complicated analog of the dots in Barnaton's category. Okay, so these are like fancy dots. All right. Okay, so let me. All right, so maybe it's a good time to actually stop now, yeah. So yeah, if you have any question, please feel free to ask.
We'll take a break until the half-hour mark. Please ask your questions.
Could you explain that ping pong table a little more carefully?
Sure.
Where's the top and the bottom?
Yeah.
Of...
Okay. So I have a table like this, right? So actually, I should have drawn it like green because it's usually green. I mean, it's often green. Okay. And then on the top of that, I have a net. Okay. So I will draw it in red, even though it's not classical. Okay. So my net is here. Okay. So you can play ping pong now. And what I'm claiming is that so you have a pair of friends which have like inverse gravity and they want to play on the table but on the other side. And so you put a net, but it's on the other side of the table. So it's on the back of the table if you want. Okay. So maybe I can actually.
Sorry, I understood that picture, but I don't understand how it's a foam. Like there is one
singular point here.
Yeah.
Okay, which is the analog of this one here. So maybe what is maybe important? Well, interesting is to look at the boundary of this guy. What is the boundary? It's the green circle here is a boundary. This guy here would be a boundary, and this guy there as well. And if you draw this, if you kind of unfold this, what you will, let me be a little bit, so I can do this and that. Okay, and this is exactly this is the same thing as that. This is just a K4 graph. Okay. So what I'm saying is that in this form, I really want to have this extra flexibility to have like more general singularity than just this one.
Can you say that on the Moy graph, two vertices collide and then?
So sorry?
There is a recombination in the Moy graph. Two vertices collide.
Yeah. Yeah. This is yeah. Exactly. So thank you, Anton. So yeah, you can see this guy as a kind of cobordism between this guy here and this guy there. So now if you want me to put some, so I can put A, B, maybe A plus, no, this was not clever, B plus C, A plus B plus C, and here A plus C, B. And here I can probably put A plus C, A, B plus C, C, I guess, and B here. So this is really what comes in between. Imagine you want to transform this guy to this guy, you just, yeah. So, but I think, yeah, thank you, Anton, for
I'm not sure it helps, but you can draw it as associativity. And that's
yeah, you can, yeah. Yeah, thank you, Emmanuel. So you can draw this like this as well. Yeah. Okay, so you have to imagine that you want to slide this along want to slide the middle point, the middle leg, and of course at one point you will have to kind of cross the trunk of this tree, and this is where the singularity is.
So in your table tennis ping pong table, where's the A, B, and C's?
Yeah, they live. Okay, so you have to be a little bit clever. So they live maybe here, and then so here I have A plus B, and here probably maybe I want to put C here, and so I have A plus C here, and here A plus B plus C.
I see.
It's double control.
All right.
Thank you.
All right. Good questions. So this is a good place to begin again.
Yeah. So okay. So now we have this. So we kind of understand the source category of the nice TQFT I want you to speak about. And so my way of actually constructing TQFT, or the only way I actually really understand, is using some universal construction. So, and for this, we'll need a black box, which is a form evaluation. And I won't explain at all what this actually, I mean, how this works, but this is from a joint work with Emmanuel as well. So I won't explain how to construct this, but this is a map from foams, and actually I should say closed foams, so they with no boundary, so the set of foams, to the set of symmetric polynomial in n variables. Okay, maybe I want to make this guy Rn. Okay, so as I said, this is a black box, so I will put it in the black box. Okay, and probably, I'm not quite sure, but so Emmanuel will probably speak about kind of an institution of that in a special case tomorrow, in a foam-free case. So it's a little bit lying here, but yeah, and probably Mike, I'm not sure, but yeah, maybe Mike will speak about that as well. I don't know. So so I want to, so I have this I have this tau n, and okay, now I want to construct this trivalent TQFT. So which is what? Which is just would be trivalent TQFT, which is simply a functor from so the category of foams and where objects are homograph and morphisms are forms to I guess category of maybe Rn projective module. I mean, it's graded as well. Well, there is a lot of graduations that I will not really speak about, but there is some kind of gradation. So this is, I want to build a trivalent TQFT from this guy, okay? And so the idea is actually quite simple. It goes back to Blanchet, Abegger, Masbaum, and Vogel. So, or maybe even before, I don't know. So if you take gamma, a graph, okay? So I need to associate a kind of Rn module to this guy. So what I do is that I first define, so maybe let me go on the other side of the blackboard. So I first define, actually, I don't know what is better. I first define the V tilde of gamma, which is, it's a huge stuff, okay? It's a direct sum of a lot of copies of Rn. These are shifted with some degrees that I won't discuss, but okay, just for the sake of it. And I take a copy for each form which goes from the empty to gamma. Okay, and now I will put a linear pairing on this guy. Okay, which will take two basis element of okay, I should say sorry. So two Rn. Okay, and so I take two basis element here, F and G, and what I do is that first I compose them. For this I need to actually reverse F, so maybe I'll draw a picture, okay, and then I can apply tau n of this guy. So just to be clear, I have my graph here, gamma. Here you have a form F which goes into gamma, and then in principle, I have this other form G, but I kind of turn it around, and this gives me gamma bar. Okay, and then I define V of gamma, or I should say actually Fn of gamma, to be simply V tilde of gamma modded out by the kernel of the, or the radical, if you prefer, of this bilinear operand. Okay, and this, then we can extend this to a functor. Extends for free to a functor. Okay, and this whole process is called universal construction. Okay, and yeah, and so okay, so the theorem here, I mean, or maybe I should say here I should say maybe proposition is that Fn is TQFT in the sense that, so what is important here is that somehow everything is finite dimensional, or actually of finite rank here, and it's a modular functor. So finiteness and modularity. Okay. So okay, and maybe the okay, so it says that Fn categorifies the exterior Moy calculus, and this is because actually if I look at the graph gamma and I apply my functor here, what I get is a Rn module, and I can compute its, so it's actually free because, yeah, so it's free, and I can look at the graded rank of this guy, and this is precisely given by this from the decategorified story. Okay, and this somehow this property is really essential for qualifying this TQFT as nice, and so the theorem is this is still from 17 is that Fn yields a link homology theory, which categorifies what it should, that is categorifying the RT of UQ SRM with symmetric powers. Okay.
Exterior.
So, and it's, sorry?
Exterior or symmetric?
Yeah, exterior power for the moment. Yeah, so this is a classic kind of, so this is exactly, so what you get is like classical Khovanov-Rozansky homology, except that here everything is equivariant, but there is no, so it's a really classical stuff. So now we want to, so as I said, I will first explain what we know in the exterior case, and then I will try to explain how to adapt it. So, okay. No, I'm lost. Sorry. What? Yeah. So yeah, and then all right. So then the question I can ask is, can we do the same thing? Same thing for the say symmetric Moy calculus. So as I said, yeah, in the, maybe I didn't say that, but in the 3 steps I described for cooking up link homology theory, the only place where actually this Moy calculus will pop up is really in the second step, and so that's why I really focus on that. And so, and now also we can really try to do the same thing for Moy calculus, for the symmetric Moy calculus, and the answer here is no, we can't. No, that's not possible. Okay, so this could be the end of my talk, but I still have 15 minutes to go. And so there is a but yes, if we restrict the category, the source category. So in other words, so my graphs are too general for my purpose. Maybe I should say something. So when I say no here, it's not that we didn't manage, it's that we have evidence. I mean, we have actually obstruction for the existence of such a nice TQFT categorizing the symmetric codes. So I can come back to that later, but it's a little bit technical, and so it's really not possible to have a setup which is as nice as for the exterior power. So I will restrict the category. So I need to find this other piece of paper. So the category I want to consider is really similar to the category we were working for, but now the objects are vinyl graphs. So vinyl graphs are my graphs, which are embedded in the annulus. Okay, and furthermore, the orientation of the arrows should always turn in the same direction. Okay. All right. I want maybe before I go to the form story, I want to emphasize something. So if I can define an index. So if I cut my vinyl graph somewhere, I will meet a couple of edges. Okay. So I don't know if you can actually see the numbers here, but here I have 2, 3, and 2. I can do the sum. So 2 plus 3 plus 2 is equal to 7. And this actually number is an invariant of the graph because of the flow condition I have on a trivial graph. So if I cut somewhere else, I don't know, maybe here I have 1 plus 6, and this is 7. Okay, so this is the index. So 7. So 7 is a magic number. 7 is the index. Okay, right. And now also, this is a graph, and the morphism we'll consider. So maybe the graph embedded in. Maybe I want to call this this annulus A, and so vinyl forms are in A times 0, 1. And they should satisfy some kind of respect this vinyl property of graphs. Okay, I don't know if this is very clear, but probably it is. I don't know. So, but here I want to make a remark which is important. So, so now I can define the category vinyl. There's an object vinyl graph and morphism vinyl forms, and this category vinyl splits as a direct sum, which is index by index. So in other words, if the index of gamma is different, of gamma 1 is different from the index of gamma 2, then the space between gamma 1 and gamma 2 is empty. Okay, so now I will actually I can consider category vinyl K where I have a fixed index K. Okay, with fixed index. Wow, okay, no, I shouldn't have written that because now the sentence doesn't make sense anymore. But okay, so we consider a category vinyl K. Okay, so, right. Okay, so now the category we consider as, okay, now I write this here. So we wish to construct a functor. So we wish this. A functor from vinyl K2. So here I will be, so we can be a little bit more general here, but let me, for this talk, just focus on this. I want to construct a functor from this category vinyl K2, the category of QUACKS. And actually what I want is that this categorifies a symmetric Moe calculus. So that, yeah. So I'll probably make that precise in a minute. Okay, so so I have one remark, so which is and I want to do this in the same way as I did before, because that's the only way I know how to cook up TQFTs. And here I have a problem. So if K is greater than 1, so vinyl K has no empty object. And somehow this empty object was important. And therefore it was important because if you have an empty object, you have closed morphism. You have morphism from the empty set to the empty set, and so you have closed cobordism. And so therefore no closed cobordism. All right. So so we need to find a replacement for that. And so the replacement is what I want to call SK. Okay. And so I don't have a, so I have my annulus here. So this would be A. Okay. And my SK is just a simple circle with label K. Okay, it's somehow it's the simplest object in this category vinyl K. Okay. All right. So so now I need so this is good. So now we need to construct an analog of tau n. Okay, and I will do this in 2 steps to actually because I want to mention Sorge binomials along the way. So I promise this in my abstract. So I have to do it. So first I will construct. And this will be denoted this. Okay, just yeah. So this is spoiler. Okay, so this will be my replacement. Okay, so but for the moment I will replace. I will cook up something like this. So it should go from a vinyl form, which goes from SK to SK, okay, to this guy will actually go to the same ring as before, so RK, so which is, sorry, it's not exactly the same ring because now it's a K and not an N. But, okay. Yeah, and so this guy it's not very complicated. So so sigma K infinity of F is simply tau K of, so I still have this F here. Oh, okay, run into trouble. Okay, and now I can kind of I can close this guy up with 2 disks. Okay, so but be careful. So this guy is no longer vinyl. But that's okay. I mean, that's just my definition. All right. So I have 5 minutes left, I think. All right. Good. So, all right. So I will try to be, okay, so now if you, okay, so maybe, so theorem. So this is, so if you apply the universal construction to the category, to the pair category venal K and the invariant, this evaluation sigma K infinity, what you get, well, so you compute the zeros homology group of some of the Sorger binomial associated with gamma. Okay. I will not define this guy here. So probably if you know what Sorger binomials are, and if you have seen some kind of graph a little bit what I drew before, you probably can understand this statement. If not, just ignore this. Okay. But I promised that I will speak about Sorger binomials, so I felt that I needed to kind of rush into that. So, but I mainly want to actually go a little bit further. Okay. So remember, what I want to construct is not this sigma K infinity, but this sigma K n, because in the end, I want to categorize the symmetric Moir calculus. Okay. So, all right. So we fix n. Okay. And then I want to, so, okay. So I will define this guy. Okay, and I fix as well f, which goes from sk to sk. Okay, so so I will define this using a recipe, so it's not really equal here. It's just like so you first express sigma k infinity of f as a linear combination of symmetric monomials in x1 xk. So maybe I can give an example of a symmetric monomial if, say, I don't know, k equal 3. So x1 square x2 plus x2 square x1 plus x3 square x1 plus x3 square x2 plus, well, I don't know what I forgot, but x2, so this is not at all. So this is a symmetric monomial, okay? And this guy actually forms a base of the symmetric polynomial in k variables, so you can definitely express this guy. Okay, so this was, okay? And now you define sigma k, n of f is the coefficient of, so x1, the product of x1 xk to the n minus 1. Okay, so that's good enough. And so and now using the same story, so so universal construction gives you yield functor that I may want to call the Sn, okay? And the theorem is that, well, I should say, this categorifies actually the symmetric Moir calculus, so somehow everything is as we want. So the quantum dimension, sorry, of Sn of gamma is, okay, I should have, so this is a symmetric Moir calculus. Okay. And this theorem says this yields, so together with step 1 and 2, 1 and 3, sorry, in the link homology theory. Theory which categorify what we wanted, theory. Okay, and so yeah, if I may take 1 more minute. Yeah. So I think it's worth it to actually say this. Maybe theorem. So okay, what is worth saying is that actually, even though I really try to convince you that everything going on here is really elementary, but we cannot prove invariance using this elementary framework for the moment. So what we need is actually to relate this construction to the triply-graded homology, and in particular we have the theorem which should have come before this one here, because we actually need this theorem to actually prove this one. But there is a spectral sequence from HHH to, okay, I should have given a name to that, to HS. All right, and this is the end, so yeah, thank you.
Okay, we're gonna have questions, but before we have questions, I figure this is a good time to make a quick announcement or two. We'll have a few questions, and then those who want to ask more questions can stay in this room afterwards. Everyone else should leave to go to one of the 5 chat rooms, which are in the email. And we're going to close down this lecture room, because until we close it down, we can't take the video and upload it elsewhere, which is why each talk is sort of in its own Zoom room, so we can upload the videos at a higher speed. So this Zoom room will close down after about half an hour. And then we'll start the new Zoom room will be available, but you can't go into talk 2 until this one closes down. So please go to the chat rooms and amuse yourself between now and then. I guess I'll make some more announcements, but I don't want to interrupt. So let's have some more questions first. Just wanted to get that very public. Okay, ask some questions. I have questions. I mean, where does this monomial come from? Like this particular monomial that you're taking the question
of? Yeah, I don't know if I should come back to the, but problem. Anyway, the whole problem is to. I mean, this is very weird, because this is definitely the most stupid basis ever for symmetric polynomials. So that's definitely a fair question in this sense. So it's really weird that we choose this. Actually, we didn't choose it. I mean, it's really imposed by the framework. So so this is imposed because you want monoidality. And so how can I phrase this? So okay. I mean, the full answer is result technical, but it's really, if you want monoidality, you want to kind of ensure that when you, well, you see, monoidality will be very weird, because somehow the 2 objects you will tensor, they live in different categories. They live in this vinyl K1 and vinyl K2, and then you go to a vinyl K1 plus K2. And somehow that's kind of the compatibility between the different sigma K infinity impose that if you want to pick up a coefficient, you need the monomial basis. So somehow it's, there are no, yeah, you have no choice. So it's very weird. So we didn't look at all at this basis before, but yeah. But yeah, somehow at one point we figured that it was the only way to go.
Thank you.
I have a question.
Yeah.
So just about the case SL2 and the standard representation, I remember in your paper you said that even then it's not the usual Khovanov homology.
Yes.
Can you say, so I assume that the difference is because, I mean, the MOY calculus is the same, but the difference is the form that you start
No.
with?
The MOI, I mean, okay, yeah. So Reshetikhin to IF invariance will be the same. Yeah, you are right. It will be both, in both cases, Jones polynomial. The reason why they are different, I mean, this is, I mean, we were really sure that they will be actually isometric, but they are different. So typically the symmetric homology is bigger. So, I mean, the rank is bigger. Okay, so I have to admit that we really have a problem to actually compute things because yeah, so we understand the dimension. We understand, as I said, we understand the dimension here, but we don't actually understand basis of this guy. And so if you really want to compute things in a homology, you need to actually compute differential ones. So for this, you need basis of your vector spaces. And so we are currently writing a program to actually deal with the case n = 1, which is already interesting. And actually, Emmanuel will speak about that tomorrow. And they will explain more in details what is going on. I don't have I don't have right now. I can't show you the homology of the trefoil, but it's because I forgot it. But it's different already. And actually, this was pointed out already by Kefelec and Rose and Sartori. So they knew already that it was different.
But the reason for the reason for the difference is from this from the definition that you start with the annulus form with this because you don't have the empty MOY graph.
No. I mean the reason is that when this homology are just different. It's just they compute different things.
Lulu, can I say something?
Yeah.
Also, if I can add, my understanding is that so first you have to work in a cylinder, so you have to work with braid closures and proportions between them, but then you have the usual dots. So you take only relations that hold for all n, some kind of stable relations, and but restricted to forms in nicely positioned in the solid torus. But then you have these dots x, but you need to convert from these dots to new variables called t, where a high power of the dot x converts into lower linear combination of coefficients in t. So there's some kind of additional conversion going on that's very subtle. And so I think to me, it took me a while to get used to, but there's some kind of strange conversion from usual dots that usually collects to this new type of maybe dots, which is coefficients called t. So you have to forget this polynomial structure with dots over x to do this conversion in some sense. So there are several steps. But at the end, you recover this symmetric homology.
I see. Can you prove that there's a spectral sequence or some other thing related to relating the two SL2 theories?
No.
No.
Okay.
I mean, maybe Emmanuel wants to say something.
Yes. I mean, there's no computation, so it's very speculative, but the guess for the moment is that the symmetric homology factorized by the homology of the unknot, and then you get a version of the reduced Khovanov homology, and then you have the symmetry to go on this conjecture of symmetry. So I mean, it doesn't kill this conjecture that the symmetric and the exterior homology should be symmetric with the change of variables into the Poincare polynomial. But since there's no computation, we cannot. I mean, they are not that different. I mean. And the other thing which is very different is that in the hypercube, for the symmetric version, the zip or the unzip are always injective or surjective. I mean, it doesn't depend on the graph at all. Whereas in the exterior case, well, it does depend. You cannot know locally, looking to the saddle-morphism, whether or not it's going to be a commultiplication or a multiplication. Whereas in the symmetric case, you always know.
So in the symmetric case for GL1, zip and unzip are both injective. Both injective?
No. In any case, for any, for whatever. Zip is injective and unzip is surjective. But I mean, that's the case already. I mean, in if you think in triply graded homology. In triply graded homology, I mean, one of the crossing, the complex of one of the crossing is always injective, and the other one is always surjective. So on the level, at the level of Sarkar-Babington, and this is somehow just a kind of instantiation of this, or quotient of this map, if you want.
And just follow up on Chiplin's question. So for GL1, you already get a very subtle theory, while in the exterior case, the theory is trivial. At least the way we would build it, it's completely trivial. But
yeah,
in the symmetric case, GL1 case is very subtle.
Yeah, it seems. Yeah. So, so as I said, so yeah, I mean, we are current. So as I said, the whole problem for computation is really finding this basis. But so this is very fresh. I mean, this was from yesterday. Sorry, we actually found the basis, and so maybe so I'm currently trying to write a program, but my programming skills are what they are, and so I don't know what. So yeah, so we hope to, but yeah, we can. This is non-trivial. This is highly non-trivial, and we don't really understand what kind of information this guy is carrying. Yeah, so.
I think this is a good time to thank Louis-Hadrien again.
All right.
And stick around and you can ask more questions. This room will stay open for a while for that purpose. Otherwise, head on out to the chat rooms and have a break.